All right, hello everyone. Welcome back to another cybersecurity Cybertruck edition workshop by the Q Project. My name's Solomon Denning, and I'm going to be teaching tonight's workshop about CBC, or Cipher blockchaining. So, first off, what is a cipher? In case you don't know what ciphers are, in cryptography, they call a cipher an algorithm that will perform encryption and decryption. So it basically just gives you a step-by-step guide that you can follow, or a procedure for how you can encode a piece of text or a message and then decode it and get the correct original text. One of the most basic ciphers that they teach you, especially if you're doing computer science and you're taking your courses on data and mathematics and all that, is they'll teach you Caesar ciphers. And this is just one of the most simple ciphers where you're literally just shifting characters. So if you have a shifting of, say, 3 characters, you would take your plain text, and every letter you would just shift it 3 letters over in the alphabet. So this picture down here on the bottom, it's a little small, but if you see the top row, it's like A, B, C, D, all the way to Z. And then the ciphertext alphabet would be 3 letters shifted. So it's in plain text, you would have the letter A, and in ciphertext, you'd have the letter D. Pretty straightforward on the Caesar cipher. And so if we move on, then we move on to block ciphers. And so the block cipher is a type of cipher, but it basically just creates pre-sized blocks and it sends your messages in those blocks. And so these blocks could be any size. It could be 128 bits, 256 bits. Those are like the most common nowadays. And it would literally just be, say you want to send a simple message like hello world. If it fit within 128 bits, you would just have one block of text that says hello world. You would encrypt that all 128 bits and then send it to whoever you want to send it to, and then they would have the same instructions on how to decrypt and get the message back. Some of the most common types of encryption algorithms nowadays are DES and AES. There's a lot of other ones, but I just put these two for examples. DES was one that kind of paved the way in cryptography, and it's been around for a long time. But because it uses 56-bit blocks, it's pretty insecure and no one recommends you use it nowadays. The more secure one, and the one that's one of the industry standards, is AES. It's like advanced encryption standard. And that one you can either pick between block sizes that are 128, 192, or 256 bits. If you see the image here at the bottom, this is just a simple way of how the encryption works with the cipher. You take your plaintext block. In this case, they're saying 64 bits, but that it could be any size depending on whatever you're using. Then you would encrypt it with a key. The key is important. You use a key to encrypt because then when the recipient gets it, they're going to be using either the same key or a key that works mathematically the same way, so that they can plug that key in with your ciphertext and then decrypt it. A better image to show this is, you should see right now. So you can see there's a sender. They have some plain text. In our case today, this plain text would be like a cipher block of a certain size. Then they would have a public key, they would encrypt, and then they would send this to whoever they wanted to send it out to. And that person that receives it will have a private key that is able to decrypt it back into plain text. This doesn't go into all the details of how this works. It's just a basic understanding so you know how encryption works. I don't expect you to have to know all the math behind this at the moment. And so moving on from just block ciphers, then there's a thing called block cipher mode of operation. This is basically just, say you have a block size of 128 bits. If you wanted to send something larger than 128 bits, it would be pretty tedious to have to split it up yourself and send out, like, say it was like 1,000 bits or so, then you'd have to send out 10 different blocks and each block would have to be made manually and sent out, and it would be kind of tedious to do that. So they have modes of operation that basically describe how you can repeat a cipher block multiple times so that you can transfer a large amount of data and have it all be encrypted and in a way to where you can easily decrypt it as well. And most of these modes of operation require something at the beginning called an initialization vector. This is because they usually take the when you when you encrypt your first block of plain text, it will usually take that first block that's encrypted and pass it into the second block and use that as a starting point for the second one as a key almost. Like I was mentioning the keys, you pass it in as a key to your new block of text. But as you can imagine, at the very beginning, when you're encrypting your first block of text, there isn't a pre-existing block to add into it. So they have something called an IV that is basically just a list or some number of whatever size, depending on your block size. And it's just unique so that you can start your encryption. And then whoever receives it is also going to have the same IV. So this is almost acting as your key for the beginning of your block cipher mode of operation. This might sound a little confusing, but I'm going to be showing diagrams of how this all works in a couple slides. So hopefully then I'll be able to explain it a little better. But the next idea is cipher block chaining. So this was the topic for today, CBC. This is a form of it's a form of the mode of operation. So there's a bunch of different ways to do modes of operation, basically combining block ciphers into multiple blocks. This is just one of them. The way this one works is by taking the previous plain text that's been encrypted and XORing it with the new one, the new plain text. And this has some drawbacks involved with it. Two of the basic ones are it's sequential. So you have to take your first block of text, encrypt it, and then pass it into your second block, which means you can't create parallelization, which they talk about a lot nowadays. Parallelization, where you can do the same task in multiple, or like split it up into multiple tasks that are running in sequence. You can't do that because you have to start with your first block that passes into the second, passes into the third. So it's a little slower. It's slower than some other techniques, but this is also one of the most commonly used ones. So it's still really well known and popular in the industry. Another drawback is the size. Because we're working with cipher blocks, if you have a message that's say like 10 bits long or 20 bits long, and you're using blocks that are 128 bits, you have to send a single 128-bit block. So if you're sending small messages, it's kind of you're wasting space or storage when you're sending. So moving on to how this works visually, so I can explain it to everyone here. You can see this image here in the very top left corner. You have your plain text. So this would be the message that you want to send. And this would be an initialization vector IV. So this would be something that's generated by the CBC algorithm. And then you would send this along to your friend or whoever you're sending it to so that they have this ready for when they receive your message. So these two things get XORed together. Basically, what that XORing means that if you have 2 bits, say you're comparing 2 bits, one's a 1 and one's a 0. If you know anything about bits, zeros and ones, 0 is for false and ones are for true. So if you're comparing 2 bits and one of them's a 0 and one's a 1, what an XOR is going to do is say that that statement is true and pass along a 1. If both of the numbers are 1, like say the initialization vector starts with 1 and plaintext starts with a bit of 1, the XOR is going to say it's false and it's going to pass a 0. You don't need to know exactly how XORing works. You just need to know like that's the basic functionality is you're taking a list of bits from the IV and a list of bits in plain text and XORing them to create another block cipher, and then that is going to be encrypted. So the output of the XOR is going to be encrypted with your block cipher encryption. This would be like AES or something else, but in this case, it's going to be through CBC encryption. And then that final message is your ciphertext. In a normal block cipher, this is where you end. You would have your ciphertext and you would send that along to your friend. But in our case, we're using blockchaining. So we're going to take that ciphertext and pass it into our second message. And the way you can imagine your second message would be, say you're sending, so what is it? Say you're sending three words like hello Bobcats for UC Merced. Your first message would have the word hello in it. This one would have, what is it? It would basically just be you're splitting your plain text into three chunks, and each one would be a certain size. So it would be like hello Bobcats, something else, and you're splitting your message up into the predetermined block sizes. So whenever you encrypt your first block, you pass that into your second plain text, and it acts as the IV now, but it's your ciphertext, and then the same process repeats. It XORs those two together, encrypts it using the block cipher encryption, passes that ciphertext along, and then at the very end, what you have is just a single block of ciphertext. And all you need to do is send that single block to whoever needs to receive it. And then whenever they receive it, they're able to reverse these steps. Since it's a procedure that goes step by step, they can do it in reverse and decrypt your ciphertext. They have to start from the very beginning though, so they're going to take your first ciphertext, they're going to decrypt it, then they're going to pass the IV into it to receive plain text. But before they encrypt this plain text, they're going to send the initial ciphertext into the second block, and then that ciphertext is sent into the next one. It's basically just it's taking this encryption method and reversing it in a basic sense. Here's an example of how this works, and hopefully after I explain this, it should make a little more sense. If not, you guys can ask me questions and I'll try and answer them. But you can see here that, say this is your message. You have 00011011, 8 bits of information you want to send, but you can only send 2 bits at a time. So this would mean that your block is 2 bits wide. This is your initial vector. It could be anything. In this case, it's a 10. So these two numbers are going to get XORed together. The reason why the output of the XOR is 10 is because it's going to look at the first bit and say, okay, this is a 1, that is a 0. This means true, that means false, which means that with an XORing of that, it's going to be true because they're different. It's weird at how it works. It's basically just an OR, but the opposite of OR. So because this is a 1 and that's a 0, it's going to output a 1. Because this is a 0 and that's a 0, they're the same thing. It outputs a 0, a false. So this is your message that you're going to want to encrypt now. And this here is the cipher table. So this would be whatever encryption method you're using. You're going to go through that encryption method. This is a really basic one, like more basic than any actual program is going to be using. But you can see that if you have a message of 10 on the cipher table here, it's telling you that the ciphertext message is going to be 11. So we went from plain text of 00 to a ciphertext of 11. And this now is going to be passed into your second block. The same process is going to be repeated. This is a 1, that's a 0. Because they're different, it's going to pass along a 1. This is a 1, that's a 1. Because they're the same, it's going to pass along a 0. And then you're going to look at this message, go to your cipher table, decrypt or encrypt it, and this process continues. Now, whenever we get to the decryption part, whenever you send this message along to your friend here at the bottom, the ciphered message, it's up here now. It goes from here to up here. It's going to be the same process, but in reverse. So you would start you start on the right side. I think I made that mistake in the last slide. I was starting on the left, but when you're deciphering, you're going to start here and you're going to grab this mess. Wait, hold on. My bad. I'm making a mistake here. It does start on the left. It starts on the left for the encryption and decryption. But you'll see that this message comes down here. It is being decrypted. So this is the ciphered message, which is the 1-1. And then you're passing it back to the plain text, which is 1-0. So that's why this is going from 1-1 to 1-0. And then if you want to get the original plain text message, you have to XOR this. So if you XOR 1 and 1, it gives you a 0 because they're the same. If you XOR a 0 and a 0, it gives you 0 because they're the same. And if you look here, this 0-0 is the same plain text as this block up here. And the process repeats all the way through. So hopefully that makes sense. If you guys have questions, let me know right now. I'll give a second or two for you guys to type up your questions or ask them before I move on. Okay, it looks like you guys are good on questions, so let me move on to the next slide. So after seeing how the encryption works on like a simple level, why would we want to use CBC and why is it one of the most common like cipher block encryptions used in the industry? For one, just blockchain in itself allows for strict data integrity. The idea that you have to pass along your first block to the second block, then to the third block, it requires them all to be they're all tied together, which means that someone can't just grab the last cipher text and try and manipulate they're not going to get anywhere with that because how would you know what the previous cipher text is and how would you know how to XOR it and all that information? It ensures that if someone receives the encrypted message, they're going to know that it's messed with if it was messed with. And if it wasn't messed with, they're going to be pretty certain that that message is secure and hasn't been manipulated. This is also why cryptocurrency uses blockchain a lot. You might hear cryptocurrency and blockchain being thrown around a lot, especially nowadays because of Bitcoin. And this is the basic idea of how it works. Cryptocurrencies, they use blockchain because blockchain allows you to store large amounts of data. So every single transaction that occurs in cryptocurrency is being stored in a blockchain type message or so that someone can send that off to someone else in case it needs to be sent off, all that. Or if you're using, uh, say you're using a company that stores your cryptocurrency for you, they're going to have large databases that are storing all of that data in blockchain, and it's going to be encrypted and secure. And then whenever it needs to be decrypted, that's what's going on with your cryptocurrency when they're doing all the hashes and everything, trying to do Bitcoin mining or cryptocurrency mining. It's because they're trying to solve these blockchains to get the information. And the reason cryptocurrency loves this is like I was mentioning, it's super secure. It has integrity. You can make sure that say you've bought in like one Bitcoin is like I think it's over like 50,000 now. You wouldn't want that information being lost, the information saying that you've bought in one Bitcoin with money. So you're able to encrypt that information in a blockchain, store it on your own computer, store it on a company server that you trust, and you can make sure that that information never changes. whenever someone goes and checks it, they decrypt it, they'll be able to know that you made that purchase and it can't be messed with. And let's see. I have a comment in the chat. It's saying, let's see, if one piece of the blockchain breaks, then the entire thing breaks. And yeah, that's the idea of the data integrity. The idea that, say, one block of the data is lost in transit, then the whole block's lost, which might sound like a bad, or not the whole block is not lost, but the whole block is not going to be able to be decrypted, which means that your data's safe. It might be bad that you can't decrypt it, but it's better that the data have integrity than it be manipulated in some way by someone malicious. And so with that, that's the end of my workshop for today. These are the sources I used in case you want to look them up. If there's any questions, I'll give a few seconds for you guys to ask them or put them in the chat right now. And if not, that will be the end of today's workshop.
So what was the, maybe you could go back a few slides to the, where it shows the common encryption methods like AES. So is it like the more bits, the more safer? Did I understand that correctly?
Yeah, in most cases, the more bits, the more safe, because if you can imagine, say you have something that's like 10 bits long and you encrypt that, it's going to be pretty simple. Like, even I can use the Ciphers or the Caesar cipher as an example. This one should explain it pretty well. Say you just have a word that's 5 letters long, like the word hello. If you encrypt that using the Caesar cipher and you give it to someone, they're not going to know what it means at first, but as soon as they hear that that's a Caesar cipher, or they assume it is, it will be pretty easy for them to go decrypt 5 letters versus you sending a message that's, say, like 2,000 words long. They might be able to decrypt it, but it's going to be way longer and it's going to take a lot more time. And Caesar cipher is pretty simple because it's just shifting letters. The rest of these, like DES, AES, they're using mathematics to encrypt, and they're using keys, so it's a lot more secure on its own. And then the longer your blocks are, the more secure it's going to be, because it requires more computation to be able to decrypt that whole block. So yeah, that in most cases, that's the reason why DES is failing nowadays, is because it's only 56 bits and it's pretty easy to decrypt it once you know how the algorithm works.
Okay, yeah, thanks. And thanks for the example that with the ones and zeros with the pathway. That was really helpful.
Yeah, I felt like this.
I have a question.
Yeah, go ahead.
Have you guys heard of there's Ethereum Classic and Ethereum, the new one? So
yeah.
Do you know about that?
Which one?
Ethereum Classic, and then the new version of Ethereum. What happened to the Classic? Why is there a Classic one in Ethereum? You know?
I wouldn't know off the top of my head. I don't keep up with like cryptocurrencies that much, but I know a little bit about them, and I think what goes on when a new one's created off of an old one is they're just like, it's using a similar like algorithm for encryption and stuff like that, but they're changing it up a little to be more secure. So I bet you if you looked into the new Ethereum, it probably has like a slightly more secure transaction part to it, or an algorithm that's a little more secure. I think that's usually what happens, or something similar to that.
That sounds about right.
Yeah, if there's any other questions, feel free to ask them right now. If not, I think that will be the end of today's workshop. So thank you all for coming. I hope to see you back here next week for another cybersecurity workshop. We host these every Thursday, and all of these are posted on YouTube. If you're watching this on YouTube, hello. Give us a subscribe and a like if you enjoy our content. and thank you.